Okay, hello everyone. Welcome to the 26th talk from the Petrolern at Home seminar series. My name is Hamid Surush. I'm the CEO of Petrolern, and I'm very pleased to introduce our today's expert speaker, Dr. Sherilyn Williams-Stroud. So before introducing Sherilyn, I really hope that you're all staying safe and healthy. We at Petrolern are incredibly blessed that we have been able to actually fill part of your time during this difficult time. It is already 4 months from the start of the P.A.S.S program, and we have brought to you 25 interesting talks from many well-known industry leaders in oil and gas, geothermal energy, and carbon storage spaces. So honestly, it hasn't been really easy. It's a time-consuming and massive work for our team to line up all these, fantastic talks. But your kind participation and positive feedback have been motivated us to continue this initiative. So far, I think we have had about 600 people signed up for the program, and they're from all over the world. And for each individual talk, we are actually having about 30 to 80 people attending each talk. It's really great. So I hope that we all pass through this difficult and depressing time safely and in good health. Before starting today's talk, I would like to remind you that our next talk is next Tuesday, July 21st, by Dr. Angela Goodman from National Energy Technical Lab from Department of Energy, titled Estimating Prospective CO2 Storage Using CO2 Screen. It's really a must-listen topic for people in CCS, carbon storage industry, and those who are interested in screening potential reservoirs for carbon storage. Please make sure you follow us on LinkedIn for updates about the now upcoming P.A.S.S talks and also other updates from our company. If you are already following us, you probably have noticed that we announced that Petrolern has been awarded funding to basically further develop and commercialize the technology that we have developed for real-time, data collection, compression, and transmission of subsurface monitoring data for carbon storage reservoirs. So we might open some job opening actually in near future to fill some of our positions in the company. So just stay tuned and check us on LinkedIn and our website for further announcements. Before introducing Sherilyn, I would like to ask everyone to mute the microphones and turn off cameras for the best quality. If you have any questions, please use the chat box to write your question at the and we read the question to Sherilyn at the end of the session. You are also most welcome to raise your hand and ask your question directly from Sherilyn at the end of the session. And Sherilyn will kindly answer the question, as many questions that she has time to answer. For any reason, if you lost your connection and you couldn't stay with us, don't worry, we are recording the session and you will have access to this basically recording tomorrow, in addition to all the previous talks recordings. So, Sherilyn Williams-Stroud is research scientist and structural geologist at the Illinois State Geological Survey and University of Illinois Urbana-Champaign. Her area of expertise include structural and fracture analysis and modeling for oil and gas and geothermal energy production, with a specialization in microseismic data interpretation and induced seismicity. She is also president and CEO of Confructus Incorporation, based in Southern California. She received her MA and PhD from the Johns Hopkins University and her BA from Oberlin College, and has over 25 years of experience in government and industry. In addition to teaching industry short courses, she has held a adjunct position at the University of Houston, California State University in Los Angeles, and Northridge. and has been a full-time faculty member at the Whiteyear, if I pronounce it right, Whiteyear College. Am I
Whittier.
right, Sherilyn?
It's Whittier College.
Oh, Whittier College. Sorry about that.
Yes.
She is an active member of several professional organizations, has been an AAPG visiting geoscientist since 2014, and was a member of the NASEM committee on seismology and geodynamics from 2015-2018. So Sherilyn's topics of talk is structural interpretation and fracture modeling with hydraulic fracturing induced events. With that said, I would like to pass it to Sherilyn to present her interesting topic. Thank you, Sherilyn. All yours.
Thank you. Yes, thank you, Hamid. Okay, so as Hamid said, I do a lot of fracture modeling, and I'm going to talk a little bit about approaches that you can take to fracture modeling. And the thing that to me sort of propelled it forward was the advent of microseismicity that we can get in the subsurface when we're doing hydraulic fracture stimulations. And I'm sure earthquake scientists have known about this for a while, that they were looking at big faults, but we can do the same thing with fractures. And in order to show you how I work through that, I'm going to give you the details of a case study that's a hydraulic fracture stimulation. But in the end, I'll mention implications for other applications such as CO2 sequestration, which I'm very active in at the moment, and any seismic hazard implications that might also be involved. So, okay, so basically, there are two ways you can model fractures, right? So you can do a deterministic model, or just it's a way of modeling geologic, the subsurface in geology anyway. Will be if you have a deterministic model, it's a model that where you define something specifically by the parameters that you measured. So in this case, you're looking at a volume, a sliced 2D seismic line where you can see there are faults. So those, if you're going to build a model, you would put those faults explicitly in the model at those locations where you see it in the data. And then there's geobodies, which you would also define explicitly. A stochastic model will be one that introduces randomness so that you can have a distribution of the properties that honors what you've measured in certain parts of your reservoir, especially in places where you don't have a lot of well data, you have to fill in between. So for instance, one of the things you can do is this is a restoration model that I did where I calculate the volume that was just restored and then redeformed so that you could model the volume dilation, and then where you have high volume dilation, you could model it stochastically and say that that's where you'd have a higher fracture intensity. And so that little box right there would be representing what the fracture distribution would look like between those. There's 6 wells there. And so you have a probability distribution instead of unique explicit values. So if you want to compare those two, if you're modeling something stochastically, you can specify orientation for fractures. So you can get that from dip meter log, seismic anisotropy, and direction. You can measure intensity based on some sort of seismic property. You can relate it to lithology. If you have fracture intensity logs or image logs, you can get it from that. And then the distribution is a little more difficult because then if you are getting your information from wells, then you have to interpolate, as I mentioned before. Or you can do something like I just did, like you measure, do something where you create a volume, you create strain, or you do geometric analyses, or you do something like proximity to faulting. So those are different ways to do distributions stochastically. But size is always an issue. Every time I have modeled fractures in the past, I was frustrated by, okay, you just have to pick a size distribution, find something that looks reasonable and think about something that you've seen in the field. But it's always a guess. It's an educated guess, but it's still a guess. So when you do deterministic models, you also have to do the orientation, but you can get it, in this case, if you have microseismicity and you have this focal mechanism data, then you actually have a deterministic orientation. And if you have, if you need intensity, you can look at the distribution of the dots to get that. And the event locations, that's actually representing the actual event location. When you see a dot, you can assume that that's where there's a fracture or a fault. But it's limited to the extent of the microseismicity. So if you don't have something outside of that, you still have to kind of fill it in. And the size this is better. Now you can start to actually get to the size by using the event energy and the rock elastic properties. And I'm going to show you how, walk you through how a way you can do that with microseismic data. So we start with the dots in the box. And this is actually dots that are, this is from the University of Illinois, the induced seismicity from the University of Illinois. I'm sorry, the Illinois State Geological Survey is running a CO2 sequestration project, and this is the Illinois Basin Decatur project, induced seismicity. And so let's just pretend that all you have here is the dots in the box. What can you do? I'm not going to do it on this data set, but what you see that, and I'm sure that when you've looked at microseismic data sets from reservoir stimulations, you think, well, what can I do with that? You know, it's just a bunch of dots in the box. Do I assume that where I have more events, I'm going to have better reservoir performance? And so the question is, how much interpretation can you do if that's all you have? And this was my challenge. I have a data set that I'm allowed to use to analyze and present on, but I was told all I can show is the dots in the box. So I'm going to show you how much I could get out of those dots. Okay, this is what the dots in the box I'm going to use look like. There's over 18,000 events. This is a 5-well stimulation. As I said, all I can show is the dots in the box, so you can't see the wells, but just pretend that there's 5 wells there. They're obviously, some of them are going to the north and some are going to the south. And you're looking at these events sized by magnitude. And the magnitude provides a relative size. In this case, the magnitude range is minus 2.7 to 0.723. So not quite magnitude 1. Everything's below magnitude 1. They're colored by strike. So this is a really nice data set to work with because we have a source mechanism for every single event in this data set. And I realize you don't have that all the time, depends on how you acquire the data. This data was acquired by Microseismic Inc. and they use a surface or shallow buried array, and that allows you enough of it, big enough aperture to determine source mechanisms for the events. The events are colored by strike. The strike range is almost north to southeast, so 0.12 to 129 degrees azimuth. And as I said, we have a full source mechanism solution for each event, which includes the type, like the volumetric, the double couple CLVD components. So we're looking at this, we're ignoring the wells, we don't have horizon tops. Now, so first thing you might do is look at the fracture orientations, and it's clear from this data set that there's something going on here where you have these northeast trends. So the wells are going north-south, and the laterals are going north and south, which is parallel to this direction. But you got these things that light up here that are obviously faults. And so if you separate the orientations for the fault zones, and then look at separate the rest of it into another orientation, and look at the source mechanism, what you find is that the fault zones are mostly strike slip, and then the red, which represents the dip slip events, and probably the sort of induced, maybe new fractures that were created during the stimulation, those are smaller, and those are oriented mostly east-west. So there you have two fracture sets, two different ways to separate into fracture sets. And so there's two subsets of, again, I just showed you the stereo net, now I'm just showing you the histogram of where these things are, where the strikes are located. So this is the number of strikes that are fault strikes. And then this other peak in the histogram is the in-between dip slip events. And these are colored by strike again. And so the strikes have the faults have the most northerly strike than the rest of the event population. So that's the first thing. That's like something that's really easy to do to create subsets of microsize of your events. But because we have the source mechanisms for all these events, we have a lot more information for each of the events. So you can look at the stress and failure details in different regions of the event cloud. And like I said, I'm separating some of them into faults and some of them into maybe new fractures. When you look at the source mechanisms, you can also look at whether there was opening mode fracturing associated with that particular fracture, or whether it was mostly shear. And that would be related to the volumetric failure. And as you might assume, the strike slip fractures have a higher than average double couple, which is the shear component of the fractures. We're going to look at now, this is, I'll replay this, but this is just to sort of orient you to the borehole, and this is an ideal sort of vertical borehole. If you have, if you're looking at down the borehole, and this is your maximum horizontal stress direction, east-west in this case, when you start to pump your fluids, you might create a new fracture which will grow out from the borehole. That would be the opening mode fracture. And then it could intersect with another fracture. And then that could also open up if it's the same orientation, or it could intersect with a shear fracture. And I think these are the kind of things that we're talking about. And when you have these source mechanisms, this is the kind of information that you can get for each of these fractures. So this is a different coloring. So when you talk about source mechanism, you also get the strike and the dip, so the orientation of the fracture plane, but you also get the direction of slip along that fracture plane. So if the slip is parallel is horizontal, then rake strike slip rake is in blue and dip slip rake is in red. And so that way you can see in the display colors which ones are dip slip and which ones are strike slip. And so what I'm going to assume here is that when you have dip slip, because it's perpendicular or parallel to the maximum horizontal stress, then these are the ones that should have higher opening mode failure. So the red should be higher opening mode failure because they're parallel to the maximum stress, and the blue should be more shear failure. And we're going to look at this part of the event cloud in a little bit more detail next. Well, sorry, that was the bottom part, but anyway, this is just showing you a cross plot of dip versus rake colored by double couple. So the double couple means it's more shear failure, and this is strike slip. So, but it's not colored by strike slip, it's colored by the amount of shear failure. And this is, the blue is shear failure, and the orange yellow is more like opening mode failure. Okay. So here's another thing that sometimes it's obvious, I guess, that people can do this, is that you can look at just the shape of the event cloud. In this case, it's very well behaved, I guess. It looks like most of the events stayed within the reservoir, except for these blue ones, these larger ones that went down into the faults, right? So you can look at that, and you can interpret a horizon top. So there's one piece of structural information. And there's the fault. Here's some more faults. And maybe this little dip right here represents fault displacement. So you could, if you could do something and fit a surface to the top of all these events, then you actually have a horizon without having interpreted it. But you know, this only worked because this was a really well-behaved microseismic data set. And then we can look at those again in depth view, looking at the slip displacement. And again, you can see the blue is strike slip, and those are the events that went down deeper, so they're following the fault planes. And it's the same picture. It's just the strike slip events are highlighted, so the dip slip events on the top are sort of dimmed out, and on the bottom, the dip slip events are highlighted, so the strike slip events are dimmed out. So you can see how well the dip slip events, most of them stayed within the reservoir zone. Okay, so When we look at fault and fracture size and aperture, as I mentioned when I started, you usually, if you don't have the information, real size information, you have to kind of, guess based on what your experience is looking at fractures and what you think is reasonable in that particular reservoir, things you've seen in outcrops on the surface, which might not even relate to what you're seeing, but you have to pick something if you're going to build a fracture model. So it may not always be realistic. But also, when we're building these fractures, we have to assign, if you're going to use them for reservoir simulation, you have to assign some type of aperture. And so what we're going to do here is assign the aperture based on the fracture size. And it's a rough relationship that may not be that realistic, but again, you have to do something. So we're going to assume that big fractures have big apertures. And so when you look at these relative sizes, we want to look at, we're going to build the sizes, in this case, based on the source mechanism. So we're going to build the fracture sizes based on the energy from the events. And when I show you this, I'm going to show you that what you're going to see is that you won't see any fractures in between the ones that are stimulated. But we know that, well, at least I believe that almost all rocks have fractures in them somewhere. So in order to get that connectivity, you probably have to include another stochastic fracture set in there, because everything doesn't get lit up by the microseismicity. So I'm just showing you a subset of what's actually there, and anything that's induced that you can see through the stimulated fractures. So how big are the fractures? This is an example of fractures that are sized by magnitude, and it's really not an accurate representation. They're colored so that dark blue is the smallest magnitude, and it goes all the way up to a sort of reddish pink. But you can barely see them because they're not that much bigger than the rest of the fractures. So now I just said I'm highlighting all the events that are bigger than -0.5 magnitude. So you can see that they're all in this fault plane, but they're still not that much bigger than the rest of the events. And so what we want to do is look at them. One way to look at them to try to get a better idea is look at them. In this case, they're sized by seismic moment. So that's representing the actual energy from that event. And you can see that there's a really big event in the middle of that line of this trend of events here that represents this fault. And there's a couple of big ones down there. So we don't want to display them like that when we're looking at our dots in the box, but this gives you a better idea of what relative sizes you're actually looking at. So I mentioned earlier the volumetric component, and it turns out that the volumetric component looks like it is more related to strike slip events. You can see some sort of trend here. So, but if you look at the dip slip events, they're sort of all over the place. So some of them are small and some of them are big, but it could be error, but it could be that these events are much smaller, so it's harder to calculate that. But anyway, so we do have a relative sort of way to look at these. So what we're going to do is build a discrete fracture network here and size the fractures based on the event energy. And when you do this, we want to remember that faulting is controlled by the stress tensor and the rock strength. So the orientation of the fault is important, and how strong the rocks are is also important. And the stress, so depending on what the orientation of the stress tensor is with respect to the fault plane will also determine what the slip direction is. And as I mentioned just before, because the failure plane size is related to the earthquake energy, we can use this really nice relationship of using the magnitude of the event because it's equal to the rigidity of the rock, so that's the rock elastic properties, times the area of the fault times the slip distance, right? And so This is a slide that I'm not going to talk about B values, but B values are another thing that you can use to try to determine of size distribution if you don't have a size distribution, you're doing stochastic. But right now, what I'm going to do is show you how to create a deterministic set of fractures. And we're going to use this relationship here, which is also down here. Okay, so going back to this slide where we have this big fracture here and some bigger fractures there, those are the faults. We're going to create a DFM where the fractures here are, the size is related to this energy using this relationship, moment magnitude times the shear modulus times the fracture surface area times the displacement length. So, and we've seen this. So the big problem here is that at first, the first thing, my first frustration was that when you're building fracture models, you have no idea what the size is. So you intersect the part of the fracture from the wellbore, but you don't know how much of the fracture you got in the wellbore, and you can't see the ends of the fracture, so you have to pick something. In this case, we still don't really have a size. So we have the rigidity in that equation, but we still don't know the size. So since we're trying to get the size, I went to the literature to find relationships between size and displacement. And there are lots of places where this is done for large earthquakes. And then McGar and Fletcher did it they extrapolated it down to experiments. And it looks like it also works for small earthquakes. So that goes down to below like -3.5 magnitude from, actually that's not slip. Sorry, that's not magnitude, but they did stick slip experiments in the lab, and the relationship still holds. So we're going to go with picking a slip displacement magnitude in order to calculate what the size is. And so the way we did it was like, so we have the moment magnitude from the events, and then using some typical rock shear moduli, plug those in, and then from that, using this relationship from McGar and Fletcher, then you can calculate the surface area. So now we can have a deterministically determined, sorry for repeating, a deterministic surface area for each fracture in your microseismic event cloud. So this is what it looks like. In this case, what I've colored these fractures by aperture. So of course the big fractures are going to have a really big aperture, but then based on what that individual source mechanism is, some of these smaller fractures also have big apertures. And the thing that was interesting to me about this was that when I look at this, it looks to me like a fault with a bunch of small fractures around it representing a fault damage zone. So these have different orientations. So when you model these fractures like this and you're doing stochastically, you'll have to pick some sort of orientation of the fractures in the fault damage zone. But in this case, they just came out, which I thought was a nice outcome for that. And then all of these are the dip slip sort of east-west fractures that we're interpreting as being induced and maybe having higher volumetric opening mode components. And so, well, let me go back to this. The first thing you might think was, like, none of them are connected. How does this explain my reservoir stimulation? And so I go back to what I said before, was like, you're only looking at the fractures that were lit up by the microseismicity. So these are the ones that have source mechanisms, but of course there's lots of other fractures in the reservoir that are probably connected to those. There's another way you can look at it as well, is if when you consider that the source mechanisms are actually only the slip patch, so the actual full fracture size could be a lot bigger. And so this is an example of a way to approach it where I just put in the same fractures and then made each of them, the slip patch is 1/3 the size of the actual fracture. So if you look at this, like right here, this little yellow patch is the source mechanism slip plane size, but this outside of this is the size of the fracture. And so that gives you a little bit more connectivity, but we still think there's more than that. So, you know, if you're going to do this for reservoir simulation, you would want to add some sort of background fracture network to get the full connectivity. But the next slide, I want to show you why this is justified. So this is from an earthquake fault map, and this is the Hayward Fault. Looking at a very large fault here and a big earthquake. But as you can see, if this is the length of the fault, you just got this piece of it that failed during the earthquake, which is a small portion of it. So I'm sort of going by that rule to decide how big the fractures actually are. The first representation was more or less the slip patch, but the whole fracture was going to be bigger. So, and what does that do for production? Well, it looks like, and as I said before, I think what's happening here is you're getting good production because you have interconnectivity for fractures that you can't necessarily see. But it's really interesting in this case, this yellow line is the production from the well that intersects the fault. And surprisingly, it's not the worst well here. Okay, it's sort of in between. All right, so if we want to talk about induced seismicity, this is also a good approach, I think, to take, because we know, because we have this relationship of rock rigidity times slip displacement and area for the magnitude of the earthquake, we can look at how big the earthquakes might be if we have some idea how big the faults in the area are. And this is one of the things that I'm working on at the Illinois Basin Decatur project, where we have induced seismicity. It's not felt seismicity. The biggest event in the Illinois Decatur area is magnitude 1.2 or so. And we want to know if there are faults bigger than that in the subsurface, and that way we would know that those faults would be able to host a much larger earthquake, potentially a felt earthquake. And after analyzing the 3D seismic volume, we're having trouble finding faults that big. And using these formulas to try to estimate failure plane size, we're still sort of in this range of Mercalli intensity 1, which is not felt. So below magnitude 3, in between 1 and 2, maybe as big as 1.5 magnitude in Illinois. And I put the whole thing here for people to see that, okay, so the stuff that was happening in Oklahoma is in this range. So magnitude 3 to 3.9 usually doesn't damage anything, but most people will feel it. And 4 to 4.9 is modified Mercalli intensity 4 to 5. You can start to get damage there, and we know that there were large earthquakes bigger than magnitude 5 in Oklahoma, and these are not only felt but damaging earthquakes. So those are the ones you want to avoid. But if you have an idea of how big the fault planes are in the subsurface using the rock properties, and you can characterize them before injection, then you have a way to estimate how big your earthquakes might get. Okay, so basically what I showed you is that there is a quantitative way to constrain fracture sizes from microseismic data, and you can generate a geologically realistic fracture network from that. And all you have to do is constrain your fracture size from the rock properties. The downside is that the fractures that you get are relatively small based on the microseismicity, but as I said, I think that there's going to be a lot of natural fractures also in there that you don't get lit up by seismicity that can add connectivity so it explains actual stimulation from hydraulic fracturing. And there's also the possibility that if the fracture is failing in mode 1 or opening mode fracturing, that the energy from that is much smaller, so we're not actually seeing those. The other proviso is that you have to calculate or assume a slip distance based on empirically derived relationships. You can't measure it, just like you can't measure the size, but what we're looking for at this in this situation is the size. So the slip distance is the thing you have to enter into the relationship, and what you choose is going to be, it should be based on realistic relationships that have been measured elsewhere. And it's possible that these relationships that were created for large faults don't work as well for small fractures or small faults in hydraulic fracture stimulations. And finally, if you can calculate the actual fracture size, then you get additional information for risk assessment. And that's it. Thank you very much.
Thank you very much, Sherilyn. It was an excellent presentation. I personally believe that, this type of geomechanics-based analysis of microseismic data is really needed, and we should have more of that, in compare with the simple approaches that industry is taking right now. So I'm seeing a few questions, and people are still asking, sending questions. So two people are asking if the data you showed in the box are public data or not.
They are not public data, sorry.
Okay, so.
Oh, well, the first box, when I said it was Illinois State Geological Survey, the Illinois Basin Decatur Project, that box, the data in that box will be public probably no later than this time next year. So that is from a DOE funded project. And we have to provide that data, make that data public when we're finished. That project's not quite finished. It'll be finished by the end of this year, but that data will be public. But it's an interesting, different box because, as you know, hydraulic fracture jobs take, you'll pump for each stage for, 30 minutes to a couple of hours. And the Illinois, the CO2 sequestration project is continuous pumping for 3 years. So, and there are less events, but they're slightly bigger.
Okay, thank you, Sherilyn. So the next question is about rigidity that you mentioned, and how is that related to brittleness? As there's a lot of actually work being done to look at the rock and how it will behave under a stress condition. So I think the question is that how you relate rigidity to brittleness.
Well, I'm actually not relating rigidity to brittleness. So, and the rigidity is just, it's the shear modulus, right? So it's the rock elastic parameter that tells you how much energy is going to be released when you slide when the two planes slide past each other. The brittleness, I feel like relates more to opening mode fractures, which might be the thing. It's related to, I think, why you can't necessarily see opening mode fractures a lot. There might be a lot of opening mode failure that you can't see, but to answer your question simply, it's a different parameter, and I'm not relating them to each other. I'm just using the shear modulus or the rigidity because this is the way the earthquake energy is calculated.
Thank you, Sherilyn. Actually, there are a lot of confusion between, among these terms like rigidity, stiffness, brittleness, frackability. So the next question is about basically faults that are induced. The induced fracture nearby major faults. Why they are not aligned with the orientation of the major fault?
Why are the induced, like the dip slip fractures?
Induced fractures, like a smaller one that are near the big faults, they have different orientation.
Yes, I think the small ones are the ones that are being created or opened up parallel to the maximum horizontal stress. Well, I'm saying I know because I know where this is from. I just can't show you, and I know that the maximum horizontal stress is east-west. So those fractures are induced, maybe new fractures that open up next to the wellbore, or are opening up away from the wellbore. So those are opening mode fractures. They're parallel to the maximum stress. What the other ones, the faults, are pre-existing features that slip because they're weak, right? So once the fluid gets into those faults or near those faults, those will slip as well, but they're not parallel to the maximum stress direction.
Okay, Sherilyn, we have a good question from Rob asking if you have taken the result to reservoir simulator, and if you did, is it possible to actually estimate or predict the future events?
That's a really good question, and that's the ultimate goal. But I actually got this data set from Microseismic Inc. after I left Microseismic Inc. And often the operators would use it themselves to go to reservoir simulation, and we weren't involved. I have done it before with other microseismic event data sets and used it to predict reservoir simulation. My experience in that reservoir behavior, but my experience in that case was there was still a lot of manipulation of the reservoir properties that needed to be done to make it work. And actually I have a publication where I did that with my two co-authors. One was a reservoir simulation guy, and the other one was working for the operator, working with the operator. That was before we had the full source mechanism solution. So it was just dots in a box, and we did stochastic fracture networks. It can be done, but I haven't been involved in it for these hydraulic fracturing projects. It's actually something that I'm working on with CO2. So to answer your question, no, but I'm working toward that.
And I think, Sherilyn, that accuracy of this type of prediction really goes back to the, how close your fracture network model is to the natural, really, natural fracture in the field. So the next question is, can we say that this approach estimates a lower bound of the fracture configuration, since the seismic processes may not be captured in the microseismic data?
Absolutely.
Good. That's it? Okay, good. I don't see any further questions, so we are really good with timing. Is anybody that wants to actually raise hand and ask the question directly? If not, we can actually close the session here. So we are receiving some thank you for you, Sherilyn, here. Fantastic presentation. Still no questions. Thank you. Okay, I think people are good. They're just appreciating your good presentation, Sherilyn. That was really good. I really enjoyed it, and hope we can actually have more interaction with you, Sherilyn, in future, and have more talks from you. With that said, I would like to thank everybody else attending the meeting. The recording will be available tomorrow on our website. And don't forget our next presentation, a CCS related talk by National Energy Technology Lab next Tuesday, 21st of July. Thank you very much all. Thank you, Sherilyn, and all have a good day.
Thank you. Everybody stay safe. Bye.
Bye-bye.